So EMC, new issues. So those of you who didn't have issues, I think you're going to move into that oh shit category. We have battery voltages creeping higher and higher, and the graphic on the right is just a list of companies that have announced and introduced vehicles with 800 volt architecture. You know, historically we had that 400 volt architecture, and things are creeping up. And there's great reasons for this, and we're not going to get into those. HBK's got plenty of videos on that if you're interested. But where I see it from the EMC is, remember I talked about that DVDT. Inverters go from 0 to inverter voltage and from inverter voltage to 0 very quickly. So if we look at this equation, that V going up increases our DVDT. Capacitances we had in our old cabling now are more apparent. So our voltage increasing, this battery voltage increasing, is going to increase my DVDT, my susceptibility to EMC, EMI. So this is scary. And if you're in aerospace or you're in agriculture, you know, those voltages are talking even higher. If you're in, you know, heavy trucks, class 8 trucks, those voltages are talking even higher. This is going to keep being an issue. So that's scary thing one. Scary thing two. This is what scares me. As a measurement person, measurement problems keep you up at night. But it also keeps me employed. Wide bandgap switches. So this is your silicon carbide, your gallium nitride. And here I just have a graphic of an inverter turn off. So we go from the voltage being high to the voltage being off in a short period of time. The current flowing to the current being off in a short period of time. And I took a manufacturer of IGBTs, silicon carbide and gallium nitride, just so I had consistent data sheets. And I looked at their turn on time, their voltage, their DVDT spec, and their DIDT spec. And what we see is that the IGBT turn on time, 1,000 nanoseconds, 1,200 volts, you know, 3.4 volts per nanosecond, 8.7 amps per nanosecond. You know, it's fast, but not scary. Silicon carbide. A lot of the inverter manufacturers, a lot of the automotive companies are going to silicon carbide. Our turn on time is 50 nanoseconds. That's about 2 orders of magnitude less. 1,200 volts, same voltage. 10 volts per nanosecond. 10 amps per nanosecond. Order of magnitude more DVDT. And then there's gallium nitride. And while these are saved for smaller devices right now, I certainly think with the large amount of inverters that are going into active suspension, into all parts of the vehicle, especially with 48 volt systems, we're going to see more gallium nitride because it's great. A lot of advantages. 6.3 nanosecond turn on time. That's another order of magnitude faster. 650 volts, a little lower. 200 volts per nanosecond, 150 amps per nanosecond. These are blaringly fast. And this is all going to result in increased EMI. If we remember our DVDT, our T goes down, our DVDT and our DIDT go up. More EMC, more EMI. And just to really beat that point home, you know, here's our two equations again. V equals LDIDT, I equals CDVDT. Battery voltage increases. We also have safety issues with that. So that's a different story. Our DVD goes up. Silicon carbide, gallium nitride switches are fast. Our DT goes down. Really hardcore math here, guys, I know. And long cables create capacitance. Loops are inductive. These are this L and C. Power levels are naturally increasing. DI goes up. So what we see is an increase in DIDT, an increase in DVDT. There's a lot more chance for that induced noise on the measurement cables. So what can we control as test engineers? What's the hopeful side of things? And the hopeful side of things is that we can control some stuff. We can control this inductance and capacitance of our measurement side. What the engineers do, like the engineers are going to give us this stuff and we have to deal with it. I know. Engineers, think about the people doing the testing. But we can control the L and the C of our cabling. Parallel paths, we can eliminate those. Loops of cable, we can eliminate those. Distance between cables, we can increase that. Maybe. These are the things we can control. So we have to think about how do we reduce that inductance? How do we reduce that capacitance to get better measurements? New powertrain are difficult to measure. We're all going to have jobs. And just to beat that home, you know, everything is more extreme in this circuit. You know, this is back to my noise circuit, right? the distances, the 1 over r squared, so the distances between the measurement and the noise producer, so the inverter cables, needs to increase. And the scary part is that the same room, if you have the same test cell, you need more distance between your cables for these new inverters. Like if you walk into the same room that was an engine cell, and then you upgraded it to a electric cell, and now you have SiC coming in or GaN coming in, you might want to just reevaluate some of your layouts. And now you have the, what is it, Occam's razor of well, now I have longer cables to make longer distance. So we might have some solutions for that. Currents induced in shields and grounds are higher. So these shields are still working, but now they're picking up more of that induced current. This is an issue because those grounding paths that used to be good aren't sufficient anymore. The shields that used to be good might not be sufficient anymore. The same test cell might experience issues you did not have previously. And I'm going to beat this horse, but high frequencies make the old cabling routes problematic, and that's just the reality. So we've covered the background, we've covered the new issues. Let's get into some of the solutions. So let's be proactive on this.